We'll start our recording. Any questions from anything that we had in our discussion yesterday on singularity functions? Pretty interesting functions. The step function, the ramp function, and the impulse function. It's interesting if you look at the impulse function. We talked about a singularity function. We said, well, they're functions where some kind of strange thing, some unusual behavior occurs at a singular point. If you look at the impulse function, and if you look at the impulse function with the definition that we used, taking u epsilon of t, there are actually two times, it's at minus epsilon over 2 and at positive epsilon over 2, where something interesting occurs, and that's where that function is discontinuous. But when you squeeze those two together, those 2 points approach each other, and then what we can say is there's only a singular place, and that is for the unit impulse function that's not shifted, that would be t is equal to 0. So we have those three functions. We don't know why the impulse function is important, but we're going to take a look at that. Today, we're going to dig into the world of Laplace transforms, talk about the definition of what a Laplace transform is. We'll see why it's important to us and why we're going to be using it in circuit analysis, but you'll see pretty quickly that Laplace transforms are pretty interesting and useful properties to use when we take a look at a derivative of a function. And so we know we were getting into differential equations in our circuits, and then we said, hey, if we just have sinusoidal inputs and we want to forego the homogeneous response, we can use this phasor transform, and that will allow us to find what the forced response is. We're still interested in the forced response, but what we're going to find out is the Laplace transform will allow us to find the forced response and the natural response, and it will do it for any type of an input, provided we can find the Laplace transform of that input. So it's valid for any kinds of inputs, including inputs of different frequencies and inputs of different kinds, so that we don't have to solve the problem using superposition in the case of sinusoidal inputs. So we're going to jump right into our Laplace transforms and take a look at what is a Laplace transform and how do we write that. So let's start by just sort of nomenclature that we're going to be using. So when we look at the Laplace transform, the nomenclature that we're going to use is we're going to say the following. So first, f of t is, I'm going to be using this general f of t. You know, and I know, that our functions are going to be these voltages, i's, currents, v1 of t, v2 of t. We tend to drop the t in that world. Here, I'm going to be very explicit and very clear. We're starting in the time domain with a function f of t, and that function Laplaces, and usually we use a two-sided arrow, it Laplaces into f of s. So where f of s here is defined to be equal to the Laplace transform of f of t. So I want you to note that what we're doing is we're going from the time domain, where time is explicit in the function, that's the f of t part, there's the time right there, it's very explicit, and then we're transforming into the frequency domain. And this is f of s over here, so this is the frequency domain. So in this world, in the frequency domain, in this world, S is frequency. And you might remember that when we were looking at the roots of the characteristic equation, for example, we had something that looked like this, s squared plus 6s plus 5 equals 0. We said, oh my gosh, we can factor that into s plus 5 times s plus 1 is equal to 0. So s equals minus 1 and minus 5. Anybody remember what we called those values of s? We called them something. Minus 1 and minus 5, they were called the natural frequencies. And I want to remind you that we know that those frequencies belong in the exponents here, right there. The same as the frequencies for sinusoids, which go here in e to the j omega t. So there's the frequency. okay? Or we can think of all of j omega as the frequency. So we're going to go from the time domain to the frequency domain. We're going to throw away time, go to the frequency domain, and work with S. Why might we want to do something like that? Any ideas? Why would we want to transform from the time domain to the frequency domain? A, because it's cool. B, because frequency begins with F, time begins with T, and F comes before T. C, the frequency domain is going to be an easier way to analyze circuits than the time domain. Which of those three do you think it is?
The last one.
That is correct. It is the last one. The frequency domain is going to be easier to solve the problems. And so we're going to work in the frequency domain because it's easier than doing derivatives and then taking higher order derivatives and then solving higher order differential equations. Now, that doesn't mean that Laplace will be trivially easy, just like it didn't mean phasors were trivially easy. The downside to phasors caused us to work with complex numbers. Differential equations never caused us to work with complex numbers. But once you get accustomed and used to working with complex numbers, it's not a problem. So let's start with the definition of the Laplace transform. So Laplace was the genius who came up with this concept of figuring out how to transform from the time domain to what he called his world of frequency domain. And so this is what we're going to look at, the definition of the Laplace transform. I'm taking a function f of t. Again, every function is not going to be f of t, but it will be a function of f of t. So that Laplace transform, we're going to call that f of s. And f of s is defined to be equal to the integral from 0 to infinity, f of t times e to the minus st dt. Now I'm going to give you some detailed information that are not important. I just want you to hear it because we're going to spend a lot of time, about a year and a half from now, taking a course in signals and systems, and we're going to spend a lot of time on Laplace transforms. And I want you to know that what we're going to do here in Laplace transforms is just going to touch the tip of the iceberg on what we can do with Laplace transforms. So the first thing I want to tell you is we are going to use here, this is called the one-sided or unilateral Laplace transform. One-sided or unilateral Laplace transform. The reason it's transform, the reason it's the one-sided Laplace transform is because no matter what f of t looks like, f of t, no matter what it looks like, we start the integral from 0 on the time axis. This is our time axis. We integrate from 0 to infinity. So we discard all of this. We don't even look at it. We don't look at what we have prior to t is equal to 0. This, we know, we've talked about this 100 times. We'll decide when we start a circuit, we'll call that t is equal to 0. And so we don't care about what happened prior to that time. There is very important information contained over here. We're just not going to use it in this course. And so the two-sided Laplace transform takes the integral from minus infinity to infinity rather than from 0 to infinity. Now, sometimes there are interesting things that happen at t equals 0. We know with the unit step function, there's a discontinuity there. We know with the impulse function, there's an impulse that occurs there. So oftentimes, when it's convenient, rather than looking at t is equal to 0, we look at either t is equal to 0 or t equals 0 plus, whichever is more convenient. So sometimes we consider 0 plus or 0 minus as the lower limit of the integral. But I'm not going to lose a lot of sleep over that, and I don't want you to lose any sleep over that either. So for us, we're going to look at basically the integral from 0 to infinity. Now, this is, I'm going to rewrite this again. So f of s equals, it is defined to be the integral from 0 to infinity of f of t times e to the minus st dt. So up here, I was starting to tell you there are some interesting things that are going on. And what's interesting here is this term right here, we know is called the kernel. And I want you to understand that this e to the minus st is both a time domain function and a frequency domain function. It is a function of t and it is a function of s. And so you can see here we integrate the t, and that's how we end up with a function of s. That's why this is f of s, because we integrate away the time and we're left with a frequency. And Laplace was brilliant in figuring out how valuable this could be to do this. So when we look at this, we're going to really need to recognize some important things. So I'm going to start to write a couple of really trivial things, which I'm going to say, oh, it's dumb. Dennis, I don't know why you're writing this. It doesn't make sense. So I'm just going to remind you that f of omega is equal to the integral from 0 to infinity, f of t e to the minus omega t dt. Okay? Or better yet, that's the Laplace transform of f of t. Okay? So if I put integral of 0 to infinity of garbage times e to the minus omega, I'm sorry, let's go back to what we have, e to the minus st dt, this is equal to the Laplace transform of garbage. And you don't know why I'm writing all of this down here, but I want you to recognize this. Okay? So whatever is here that multiplies to the minus st, take the integral over time from 0 to infinity, it's the Laplace transform of whatever that is. As long as all of the rest of this looks the same, it's the Laplace transform of that. So if I wrote the following, the integral from 0 to infinity of g of t plus 22 e to the minus st dt, this is equal to the Laplace transform of g of t plus 22. So this can change, and as long as all this remains fixed, then this integral is the Laplace transform of whatever I've underlined. At the same time, we called this f of s, going back to the f of s part, and we said f of s was equal to the integral from 0 to infinity of f of t e to the minus st dt. I'm going to remind you, there's an s, and that s corresponds to that s. So I can also change that. So I can do the following. If I have the integral from 0 to infinity, f of t times e to the minus s plus, let's do something cool like alpha, s plus alpha, all times t, dt, that must be equal to f of s plus alpha. Okay, so we just recognize whatever multiplies, there's a negative, that's got to be there. There's a t, that has to be there. I integrate away the t. There's the function, okay? So here, that is f of s plus alpha. So I just want you to recognize that right now so that later on, when we start to look at some properties, we're going to start to understand what some of these properties mean. All right, so now here's what we're going to do. We're going to look at some functional transforms. What do I mean by that? I want to look at some functions in the time domain that we have, and I want to figure out what is their Laplace transform. So here's what we're going to do. We're going to build a table of Laplace transforms that you can look them up, so that when I give you a function, instead of computing it by taking the integral, you just go to the table and you say, oh, here's the Laplace transform, it's equal to this. So I'm going to start building up a table of Laplace transforms. I'm going to start with a few. Then I'm going to start to look at some properties of Laplace transforms. And then I'm going to use those properties to develop some more functional transforms. Because ideally, what we're going to do in the Laplace world is we're going to recognize certain functions in the frequency domain. We're going to recognize them and immediately be able to transform them back into the time domain. Okay, so to that end, I'm going to start with my favorite function, the unit impulse function. Favorite because the impulse function is really easy to have in an integral. So I want to look at the Laplace transform of delta of t. And that is equal to the integral from 0, and now I'm going to do 0 minus to infinity. Why am I doing 0 minus? Because the impulse occurs at 0. I want to make sure that I include that impulse in my integral. So it's going to be delta of t times e to the minus st dt. To solve this, I use the sifting property of the impulse function. Do you remember the impulse function sifting property? So this function is multiplying the impulse function. So what it does is it sifts it out of the integral, e to the minus st, and evaluates it where the impulse occurs. Evaluated at t is equal to 0. That impulse occurs at 0. And so that is equal to e to the minus s times 0, which is equal to e to the 0, which is equal to 1. So there is our very first Laplace transform. So Laplace transform, delta of t, Laplace transforms into 1. It's our first one. Now we're going to try to build up a table of these. But I'll box up the ones that we're going to place into our table. And you actually have the table in your book. There are a couple of Laplace transforms that are not included in your table. I'm going to recommend that you write them in your book. But there's our very first one. I'm going to do another one, but this one is particularly easy. Laplace transform of delta of t minus a. And I'm going to restrict this. And the restriction is going to be that I want a to be greater than 0. Any idea why I want a to be greater than 0? So a is a constant. It's real. A is real and it's a constant. Every time we take a function in the time domain, it's always real. Why is my restriction going to be a is greater than 0? Any idea?
Is it because it'd be out of the range of the integral?
That's correct. If a is less than 0, the impulse is going to shift over here onto this side if a is less than 0. So we want to make sure the impulse shifts over here. We want it to be in the range of the integral. That was well stated. Jordan, was that you?
Yeah.
Outstanding. Yes. So I want to make sure it's in the integral. Otherwise, if a is less than 0, what is the Laplace transform of delta of t minus a if a is less than 0? Any idea?
Is it 1?
No, it's 0, right? Because the impulse is over here, but we're only taking the integral from here to here. So the function, the Laplace transform, the delta function is 0 out here. So it's 0 times e to the minus st, that's 0. And now I'm taking the integral of 0. So it would all be 0. That would be uninteresting. So this one is equal to the Laplace transform is the integral from 0 to infinity, delta of t minus a times e to the minus st dt. And so we know it's still the sifting property. So it's going to sift it out, e to the minus s t evaluated when t is equal to a. That's where the impulse occurs. The impulse occurs at t is equal to a. And so that is equal to e to the minus sa. So there's another transform. I'm not going to box this one up because we're going to have a property that will allow us to see that. But the Laplace transform of delta of t minus a, that Laplace transform is e to the minus sa, provided a is greater than 0. We said what it would be if a was less than 0. If a is less than 0, it's 0. So that's our first Laplace transform. And the reason we're taking that one is not just because the impulse function is important, because it's easy to integrate an impulse function. Number 2, the unit step function. So the unit step function, so the Laplace transform of u of t is equal to the integral from 0 to infinity, u of t, e to the minus st dt. If you've never integrated with an impulse function in the integral, so if you're looking at it, those who are really good at calculus go, oh crap, I don't know, I've never seen a u of t in an integral, I don't know what to do. Always remember the following. U of t is 1 for t greater than 0, 0 for t less than 0. So we can break this integral up, or it's already broken up nicely for us because it starts at 0. So what is u of t everywhere in this integral? What is u of t everywhere in the integral?
1.
Excellent. So I'm just going to replace it by the number 1. E to the minus st dt. Now, this is an integral of a function that we love. It's the exponential function. I don't know about you, but I love exponentials. So that's going to be equal to 1 over minus s, e to the minus st, evaluated from 0 to infinity. And here we're going to do a little bit of hand waving, so you're going to have to forgive me for hand waving. You don't know anything about s right now, but s can be any complex number. It can be any complex number. And so later on, when we do work with Laplace transforms in our linear systems course, in our signals and systems course, we're going to look at different values of s. But here we're leaving s as s. We're not going to think too much about it. And we're going to say the following. So this is 1 over minus s. Now, when I put infinity in for t at the upper limit, I have e to the minus infinity times s. What do you think e to the minus infinity times s is? That's an e to the minus infinity. And what's the value of e to the minus infinity? That's correct. 0. It's equal to 0. And then at the lower limit, I plug in 0. E to the minus 0. That's 1. And isn't this a beautiful thing? This is equal to 1 over s. So our second Laplace transform is the Laplace transform of u of t, and u of t Laplace transforms into 1 over s. Okay? There are regions of convergence. We have to look at particular things. So for example, I know you're all sharp. Let's just scroll back. If s was equal to -1, for example, if s was -1, then when I put infinity in the upper limit, I have e to the minus a minus 1. That minus times that minus 1 is plus 1. Right there, that's plus 1. Times infinity is e to the positive infinity. And you and I both know that e to the positive infinity is not 0, it's infinity. So this doesn't converge. So we have these regions of convergence. And so for what values of s will this converge? S is a complex number. We have to focus on the real part of that complex number. We're not going to do that here. We're going to ignore all of that. We're not going to worry about the region of convergence. So we'll save that for later. but there are really interesting things that we can say about the region of convergence. So right now we have two Laplace transforms. The Laplace transform of the impulse function is equal to 1. The Laplace transform of the step function is equal to 1 over s. Let's continue. What do you think I'm going to do third? Take a guess.
Ramp.
You got it. The unit ramp function. So keep in mind the ramp function is r of t, and r of t is nothing more than t times u of t. The reason I want to point these things out to you is because this is a t multiplier. We have this function already, and here's its transform right up there. And now what we're doing is we're taking that function and we're multiplying it by t. And some interesting things happen when we multiply by t. Don't worry about what they are right now. We'll develop that property later on. So here we go. The Laplace transform of t times u of t is equal to the integral from 0 to infinity of tu of t times e to the minus st dt, right? It's always put the function in. I just want to point this out to you. Put the function in, multiply that function times e to the minus st, and integrate away the time from 0 to infinity. So no matter what anybody asks you to find the Laplace transform of, find the Laplace transform of dog, the integral from 0 to infinity of dog times e to the minus st dt. That's all we do is just substitute it, and that gives us our Laplace transform. Okay, so some of you are rusty with your calculus, and some of you have not had Calc 2. So just follow along, jot it down. You are not responsible for this work. You are responsible for the result. So I'm going to integrate this by parts, okay? And so I'm going to remind you, for those who need a reminder, I'm going to remind you how we integrate by parts. Before we do that, does everybody agree that I'm going to substitute, since I'm integrating from 0 to infinity, what is u of t everywhere from 0 to infinity? Except 0. This is why your author would say, well, just integrate from 0 plus. I'm not going to worry about it. We're integrating from 0. What's u of t everywhere from 0 to infinity?
1.
Good. So just substituting into 1, everybody knows multiplying by 1, I don't even have to write it in there, correct? So I'm not going to. I think you all know that. I'm not going to write it in there. So I have that. So now to integrate by parts, remember, integration by parts looks like the following. The integral of u dv is equal to uv minus the integral of v du. So what we have to do is we have to establish what are we going to call our u and what are we going to call our dv. Once we have that, we have to differentiate u to find du, and then we have to integrate v to find v. So I'm going to let u, for this example here, and down here, I'm going to let u equal t, and if u is equal to t, then du is equal to dt. Okay? In other words, what we're saying is du dt is equal to 1, but I want du. Du dt is equal to 1, right? Du dt is equal to 1, multiply both sides by dt, 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 cancel, cancel, and there I have it. Du is equal to dt. That's where that comes from. Okay, what's left? Everything that's left must be dv. So everything that's left is e to the minus st dt. Now I'm going to integrate both sides. So when I integrate, integrate, and when I integrate dv, I get v, and when I integrate e to the minus st dt, I get minus 1 over s times e to the minus st, and then I'm going to utilize that information to put together into this equation. So now my integral, the integral of t e to the minus st dt from 0 to infinity is equal to, so It's u times v. So this whole thing is the integral of u dv. Check it out. U, that's the t part. And then dv was that part. And there is the rest of that right there. So this is equal to u times v. So that's t times minus 1 over s times e to the minus st. Okay, and all of that, I have to include my limits. Don't forget, we have to include the limits everywhere. Minus the integral of v du. Integral, 0 to infinity, of v minus 1 over s, e to the minus st, du, du is dt. And of course, I've done this before, and I'm pretty good at calculus, so I knew this was going to work with integration by parts. Sometimes you do integration by parts, and it doesn't solve the problem for you. So let's look at the first part. Gosh, my arm keeps getting on these things at the top. Okay, so here we go. This is equal to, for the upper limit, I'm plugging infinity in up here, and at the same time, I'm plugging infinity in over here. Okay, so when I plug in infinity here, I get 0. Which dominates this t. So the upper limit is going to give me 0 when I do that, okay? So that's going to give me 0. And then when I plug in the lower limit, I get 0 from here. So 0 minus 0. Now this minus, I'm going to pull it outside with this one. That gives me a plus. Just going to rewrite it. The 1 over s is a constant. It comes out of the integral. And now I have the integral of e to the minus st dt. The integral of e to the minus st dt, I think we just did that. Way back up here somewhere. There it is, the integral of e to the minus st dt. And that is all 1 over s if we do all of that, right? So that is all times 1 over s. So all of this is equal to 0 plus 1 over s squared. So here's our Laplace transform. The Laplace transform of r of t, which I want to write this way because it's critically important that you see this. It's tu of t. That transforms into 1 over s squared. We're going to see this later, but I want you to think about this. A t multiplier. This function, the Laplace transform of u of t, is this. A t multiplier ends up getting me another s in the denominator. Pretty interesting result. So let's box that one up. So we now have 3. The Laplace transform of delta of t is 1. The Laplace transform of u of t is 1 over s. The Laplace transform of tu of t is 1 over s squared. And that's our unit ramp function. So 3 of them to box up, but there are still a couple more that I want to do. The next nice one that is easy for us to do is the exponential function. So number 4, let's look at the exponential function. So Laplace transform of e to the minus at. Now you and I know from a circuit, a in a circuit is usually negative. I'm sorry, a is a positive quantity, so that the homogeneous response has a decaying exponential. So in general, when we see this, a for us is generally going to be a positive quantity. It's equal to the integral from 0 to infinity e to the minus at, e to the minus st dt. That's cool. That's the integral from 0 to infinity, e to the negative, and then this is, I'm going to write it this way, s plus a times t dt. Okay, so I have 2 exponentials, so I just add the exponents together. So I'm adding the exponents, it's minus st plus a minus at, factor out the minus, factor out the t, and then I have an s plus a. Okay, that's what all of that is. That's that exponent right there. Okay, that's still easy to integrate. That's equal to 1 over minus s plus a e to the minus s plus a t evaluated from 0 to infinity. Again, assuming this converges when t is equal to infinity, assuming it converges. When I plug in infinity, I have a negative infinity, e to the minus infinity is 0, and then at the lower limit, e to the 0 is 1. So all of this is equal to minus 1 over minus s plus a, which is equal to 1 over s plus a. So the Laplace transform of e to the minus at is equal to 1 over s plus a. I'll tell you the way I like to write these when we're worried about whether or not we're doing the one-sided, the two-sided Laplace transform. And your author does a lot of this in the textbook. E to the minus at u of t. Laplace transforms into 1 over s plus a. Okay, your author likes to throw the u of t in there. Make sure we're not getting anything on the negative side of the t-axis. Okay, those were all fairly easy. I want to do one more functional transform for you. And that functional transform is, I'm going to select one of the sinusoidal functions. You tell me what you want me to do. First one to chime in. Do you want me to do the sine or the cosine?
Cosine.
Cosine it is. So let's look at the Laplace transform of cosine of omega t. So remember, we'll know what omega is when we see, just like when we see this exponential up here. Just a quick example. So we just did an exponential of e to the minus at. So this means that the Laplace transform of e to the minus 6t is equal to 1 over s plus 6. Okay? That number there goes right down there. Right here, I'm going to do it for general omega, and then we're going to plug in values for omega. Okay, so this is equal to the integral from 0 to infinity, and it's going to be cosine of omega t all times e to the minus st dt. So we've got a couple of choices. Those of you who remember integration by parts, you'll remember that we're going to integrate by parts and we'll integrate around in a circle, and that takes us a couple steps to do that. So I'm not going to do that. Instead, I'm going to refer back to, don't forget, recall that cosine of omega t is equal to e to the j omega t minus e to the minus j omega t divided by 2. Don't forget that. So I'm going to substitute that in there, and then I'm going to break it up into two separate terms. So this Laplace transform is equal to the integral from 0 to infinity of e to the j omega t minus e to the minus j omega t. I'm sorry, this is a plus, not a minus. That's a plus right there, divided by 2. All times e to the minus st dt. I'm going to pull out the 2. Equals 1/2 integral 0 to infinity. And this is going to be, I'm going to multiply this one times this one. So e to the j omega t times e to the minus st plus e to the minus j omega t times e to the minus st. All of that dt. And you know that's an integral of the sum, so I can break that into the sum of the integrals. So this is 1/2 the integral 0 to infinity. I'm going to multiply those two together. How am I going to multiply them? I'm going to add the exponents. When I add the exponents, I get the following. Adding the exponents. So I have e to the minus, I'm going to pull out a negative, and it's going to be s minus j omega times t. Double check that, make sure you agree with that. E to the minus st, e to the minus j omega is e to the positive j omega t. That's that first term. That's good. So all of that, dt plus 1/2 integral 0 to infinity, and that's going to be e to the minus, and then I'm going to have an s plus j omega t dt. And now I'm going to integrate those. Those are just two exponentials. And yeah, they've got complex garbage up in the exponents, but we can deal with that. Equals 1/2, leave that there. 1 over minus s minus j omega, all times e to the minus s minus j omega times t, evaluated from 0 to infinity, plus 1/2 1 over minus s plus j omega e to the minus s plus j omega times t, and that one is evaluated from 0 to infinity. I just want to remind you, everything we're doing here, it's not new. What's different is I have complex quantities inside of my integral. We're not used to that. But everything is all material that you've worked on and seen before. These are integrals of exponential functions. Okay, we're going to substitute in the upper limit. So first, I'm going to do the following. I'm going to take the first term, and I'm just going to write this the following way. I'm going to put the 1/2 in the numerator with the negative sign. I'm going to write this as s minus j omega in the denominator. And then I'm going to I'll plug my infinity in here, okay? This negative with that is going to cause this to go to 0. You might be asking, what about this? I'm going to just tell this to you right now. E to the j omega t, remember, e to the j omega t has a magnitude of 1. Has a magnitude of 1. It is an angle which is equal to omega, but it is a magnitude of 1. So this is a small number. So when t goes to, when I get this t is infinity and I get this minus with it, that's going to cause all of this to go to 0. So you might be looking at it thinking, well, wait a minute, that negative makes that a positive, but this is a small number out here. Its magnitude goes to 1, and so this is going to dominate the term. So it's going to cause it to go to 0. And that's when I have t is equal to infinity. When t is equal to 0, again, I have a 1 there. Same thing's going to happen on the second one. Plus numerator, negative 1/2. So I've taken care of the negative sign here and the 1/2. That's plus j omega. And then I'm going to end up with the same exact thing over here. I'm going to end up with 0 minus 1. Okay, pretty interesting. Factor out this negative 1 multiplied by that is going to give me a positive 1/2 s plus j omega plus 1/2. I'm sorry, this first one is s minus j omega. S plus j omega. And this is really kind of interesting when we look at this. So how do we want to handle that? Common denominator, right? So 1/2 times s plus j omega plus 1/2 times s minus j omega. And that's all going to be over what? S minus j omega times s plus j omega. You'll notice in the denominator, the s minus j omega, the s plus j omega looks like we're multiplying by a complex conjugate. In the numerator, let's look at the numerator. 1/2 s, 1/2 s. That's a full s right there. J omega times a half minus j omega times a half disappears, it's gone. In the denominator, we're just going to get s squared plus omega squared. Amazing result. There it is. The cosine of omega t transforms into s over s squared plus omega squared. Example, cosine of 5t. What's the Laplace transform of cosine of 5t?
S over S squared plus 25.
Beautiful, Jack. Indeed. S over S squared plus 25. Okay, so those are the transform properties I'm going to start with. There are several others in the table that I could prove to you, but I prefer to spend our time working on properties and looking at the properties and having those properties, and then with those properties, figuring out what the Laplace transforms of those functions are. So I think what we'll do there then is we'll break right now. And while we break, what we'll do is we'll take about 5 minutes. I know usually I say 5 minutes and then we take about a 7 or an 8 or a 9 minute break, but we'll try to stick to a roughly 5 minute break today. We'll take 5 minutes, we'll come back, and then we'll start looking at these properties of Laplace transforms and how we can utilize properties, knowing certain Laplace transforms, then utilizing properties, finding Laplace transforms of new functions. That's what we're after. So when we come back, we're going to take a look at that, finding some of the properties that will allow us to find Laplace transforms of other functions. All right, let's take a 5 minute break. I'm going to pause our recording and then we'll come back in 5. Ready to roll? Everybody there?
Yep.
Yep, good.
Yeah.
Terrific. Okay. So let's start to look at what it looks like to deal with properties of Laplace transforms. So the way we deal with those is we refer to the integral for the most part and try to recognize something about the integral, which is why I spent a little bit of time up front with you earlier talking about that. So let's start with these properties. And we'll start with two of the most basic. They're both related to linearity. So in order for a transform to be linear, it has to satisfy two components. And so first I'll give you one component, the multiplicative part, and then second we'll give you both the multiplicative and the addition part, addition or subtraction part. I want to point out, just so we're all clear, a Laplace transform is called a functional. It's not a function, it's a functional. It operates on a function. The result of that operation is a function. So this is a function, f of t. And when I use this function, this function operates on a value like f of 6. And when I put in 6, whatever that function is, I get an answer, which is a number. The Laplace transform doesn't operate this way. The Laplace transform takes in a function and spits out a function, and that is called a functional. That's what we have here. That's what we're working with. We're working with a functional. Okay, so let's take a look at the first property, and that property is multiplication by a constant. And I think this is going to behave exactly the way you would expect it to behave. So if f of t Laplace transforms into f of s, if it does, by the way, not every function has a Laplace transform. Some of them, the Laplace transform doesn't exist. And we're not going to talk about that in this course, whether or not a Laplace transform exists. But there are times when a Laplace transform for a function does not exist. But if this one does, then a times f of t Laplace transforms into a times f of s for any constant a. Any constant a, even complex. Probably never want to do that. So I'm going to prove this, but tell me what this result would mean. What's the Laplace transform of 7 u of t?
Seven.
Almost. What's the Laplace transform of u of t?
Seven over s.
Yes. 7 over s. And that's exactly what you'd expect. All right, now let's prove that. So we're going to do a handful of proofs today. I want to remind you again, you're not responsible for the proof, you're responsible for the result. This part up here, this is what you're responsible for, right there. You're not responsible for the proof. I'm going to show you the proof so you can see these things and how we calculate these. Some of those later courses will be taken that we've been talking about, you'll be required to develop some of these proofs. So, Laplace transform of a, I used a up there, a f of t. The definition is the integral from 0 to infinity of a times f of t, all that multiplied by e to the minus st dt. Wow, this one's too easy. A is the constant. What can I do with a with regard to the integral?
Pull it out.
Pull it out. There it is. Comes out of the integral. Integral 0 to infinity f of t e to the minus st dt. Look at that integral. What is that integral equal to?
One.
Not 1. Watch this. I'm going to scroll way back. What's that integral equal to?
F of s.
F of s, that's the Laplace transform of f of t. It's f of s. So that is equal to f of s. So all of this is a times f of s. And that's what we were trying to prove, that the Laplace transform of a f of t, so the Laplace transform of capital A f of t is equal to AF of S. Proven, done. Now we can use it. All right, I'm gonna call on people. So I want to know, Jack first. Jack, I want the Laplace transform of delta of t.
Just one.
Good. Okay, Misael, I want the Laplace transform of 4 delta of t.
Would it be 4?
Bingo. It's actually 1 times 4 or 4 times 1, right? It's 4 times 1. in the notation that we used up here, right, a times f of s. So f of s is 1. It's 4 times 1, which is equal to 4. Correct. Okay. Garrison, I want the Laplace transform of e to the minus 12t. Not sure. Okay, that Laplace transform is 1 over s plus 12. Okay, if that's 1 over s plus 12, Jordan, I want the Laplace transform of minus 6 e to the minus 12t.
Is it 6 over s plus 12
Almost.
minus 12?
Nope, that s plus 12. This minus is going to stay with the number. Keep it with the number, okay? So it's minus 6 over s plus 12. So the constant here is a, it's minus 6. So that whole thing comes over with us. Okay, and now we have Connor. See if you remember the Laplace transform of t u of t.
1 over s squared.
Beautiful. Stay on the line, you get 2 of them. What is the Laplace transform of 3t u of t?
3 over s squared.
Excellent. Arushi, what is the Laplace transform of 10t u of t? Anybody want to help her out?
Is it 10 over s squared?
Yes, it is 10 over s squared. Okay. So notice we didn't do any integration to find this. We knew this Laplace transform. We just had this number in front. And so instead of going through the integral, we just take that number and multiply on the other side, whatever the Laplace transform of what's circled. So an easy concept. Similar to that, we're going to have the following property of linearity. I'm going to combine 2 properties together. So 2, linearity. So I'm going to use both of them. If f of t Laplace transforms into f of s and g of t Laplace transforms into g of s, so there are 2 of them, then a f of t plus b g of t, I'm sure you can guess it, Laplace transforms into a f of s plus b g of s. You'll see this one break out very easily. Let's do this proof. So looking at the Laplace transform of a f of t plus b g of t. By definition of the Laplace transform, that's the integral from 0 to infinity of a f of t plus b g of t times e to the minus st dt, which equals the integral from 0 to infinity a f of t e to the minus st dt plus the integral 0 to infinity of b g of t e to the minus st dt, We already saw these from before. I can pull the A out of this one, and then that's the Laplace transform of f of t. Pull the B out of here. That's the Laplace transform of g of t. So this is A f of s plus B times g of s. Let's utilize this property. So what's the Laplace transform of 6u of t minus 3 delta of t plus r of t? I've expanded this. This had 2 of them in there. Now I have 3 functions. But you can expand into 4, 5, 6, 7, 8, 9, and an infinite number of functions. So it's the Laplace transform of 6u of t. So that's 6 over s minus 3 times the Laplace transform of delta of t, which is 3 times 1, 3, plus the Laplace transform of r of t. Laplace transform of r of t is 1 over s squared. If we wanted to form a common denominator with this, which is what we're going to do later on with our functions, we can, but right now we'll leave it just like that. That's a great form for us. We leave it exactly like that. What if we had something like the following? That Laplace transform is, just so we're clear, it's the Laplace transform of e to the minus 3t plus twice the Laplace transform of e to the minus 5t. This is equal to 1 over s plus 3 plus 2 over s plus 5. Typically, we'd like a common denominator. You'll see why later. You won't see that right now. So this is going to be s plus 5 plus 2 times s plus 3, all divided by s plus 3, s plus 5, which is equal to 2s and another s, 3s, 5 and 6 plus 11 divided by, and just leave this in factored form in the denominator. We generally like it in factored form. Okay, so that's using the property of linearity. That's a wonderful property. Now, let's look at differentiation in the time domain. Okay, what does that property say? It says, if a function, f of t, Laplace transforms into f of s, if it has a Laplace transform and f of s is its Laplace transform, then f prime of t, the derivative, this prime, the derivative, Laplace transforms into s times f of s minus little f at 0. Now, a lot of books use 0 minus or 0 plus here. I'm just going to use, again, I'm going to stay consistent. I'm just going to use 0. So don't worry about it. Don't worry about the 0 minus or the 0 plus. F of 0. Let's prove this before we use this example. So to take this Laplace transform, I have to put it in the integral, f prime of t. So just remember, f prime of t is d dt. So we're taking the derivative of that function. Believe it or not, this one integrates by parts very nicely. So we're going to integrate by parts. So we're going to let u equal e to the minus st. And then dv is equal to f prime of t dt. So du must be equal to, the derivative is minus 1 over s e to the minus st dt. And v over here, v is just equal to the integral of the derivative, which is f of t. Okay, let's see how that works for us. So then the integral from 0 to infinity of f prime of t e to the minus st dt is equal to u times v. So e to the minus st times f of t, all of that evaluated from 0 to infinity, minus the integral of v du. So the integral 0 to infinity of v f of t times du. Du is minus 1 over s e to the minus st dt. Now this is where you just have to, at some point, get used to these Laplace transforms and what's taking place. This 1 over s, I know it's a function of s, but this integral is on t. So negative 1 over s is a constant with respect to the integral. It's a constant. So we can pull it out of the integral. So let's see. This is, let's take the first one first, and let's write in there, when I plug infinity in at the upper limit, I have the function f evaluated at infinity. It's a function, and evaluating it at infinity, that is a finite value. A function is a finite value. Then I multiply by e to the minus infinity, that's 0. At the lower limit, when I plug in 0, I get e to the 0, which is 1, right? So I get e to the 0, that's 1, but it multiplies f of 0. Now, this negative, and then bring out the minus 1 over s, those negatives are going to cancel, and then I have the integral from 0 to infinity of f of t e to the minus st dt. We're going to see this a zillion times. What is that integral equal to?
F of s.
F of s. So I have a mistake there somewhere. My mistake. Nobody caught my mistake. Help me with my mistake. Right here on this line. du. I took an integral, not a derivative. The derivative is not negative 1 over s. What's that derivative? What term comes out front?
Negative s.
Thank you, Jack. Negative s. That's correct. So this should be a negative s here. So I apologize. I'm going to clean this up in this integral. This is a negative s. That makes this a negative s. I apologize for that mistake. So the negative and the negative cancels. It's a positive s. What's blocked in there is all f of s. And then all the rest of this is minus f of 0. Which is what we set out to do. Right there. That's what we set out to do. So the derivative, f prime, transforms into s times f of s minus f at 0 minus. Okay, let's try some cool things. So first of all, let's see if we agree with the following. Do we agree that that there's a relationship between u of t and the impulse function delta of t and the ramp function r of t. So here's u of t. So let's look at this and this. So if I integrate the unit step function, if I integrate it, I get the ramp function. Or if I differentiate the ramp function, r of t, then I get the unit step function. If I differentiate the unit step function, I get what function? Okay, if we go this way, we just integrate. We saw that. Integral, integral. So I'm not going to focus on the integral because all properties on the derivative. All right, so let's check. So we know r of t, which is equal to tu of t. We know that that has a Laplace transform that is equal to 1 over s squared. So from this, therefore, the Laplace transform of u of t, which is equal to the Laplace transform of r prime of t, should be equal to s times 1 over s squared minus r at 0. What's the value of the ramp function when t is equal to 0? Ramp function. T is 0 right there. What's the value of the ramp function when t is equal to 0?
0.
Good. So this is equal to 1 over s. Is that what we already knew about the Laplace transform of the unit step function? I'll answer that for you. Yes, it is. That's in our table of transforms. We knew that transform already. So we have that one. So now let's continue this example. So the Laplace transform of delta of t is equal to, well, what do we have there? Here, the Laplace transform of this is the Laplace transform of u prime of t. Now this u prime of t, remember we had that discontinuity, so we had a little issue, and I think you're going to see the issues you have with these discontinuities. So this should be equal to s times 1 over s minus u at 0. This is why I told you when we look here in this relationship that most people inside of here put a 0 minus. So let's go here and see why they put a 0 minus. So as we go back to our function, what we're looking at is u of 0. Now here's a reminder for u of 0, a reminder that you don't need, I'm sure. U of 0 looks like the following. And when t is 0, we didn't even give it a value. You remember that? There's no value to it. So look at this. This is why we want to look at u at 0 minus. What's the value of u at 0 minus? Zero minus is somewhere right over here, somewhere. And that value of that function is 0. So This tells us that the Laplace transform of delta of t is equal to s times 1 over s, which is equal to 1, which we have already computed. So we already knew that. Great. Now let's use one that we don't know. So we know the following. We know the Laplace transform of cosine of omega t is equal to s over s squared plus omega squared. That's interesting. Okay. So we know that the sine of omega t, see if you agree with this, the sine of omega t is equal to minus 1 over omega times the derivative of this cosine function. So we know we take the derivative of the cosine, we get a minus the sine, but that omega comes out front. So what we're saying is the derivative ddt of cosine of omega t is equal to minus omega sine of omega t. So solving for sine of omega t, I just divide both sides by minus omega. And so divide by minus omega gives me 1 over minus omega, which is the same as minus 1 over omega. So there we have it. Sine of omega t is equal to that. Beautiful. We already know how to handle this because that's our first property, multiplying by a constant, right? That's just a constant. All right, so we know then that the Laplace transform of minus 1 over omega times the derivative of cosine of omega t is equal to minus 1 over omega times the Laplace transform of the derivative of cosine omega t. Now we'll use the properties. Minus 1 over omega. Now, the derivative is going to be s times the Laplace transform of cosine of omega t. So that's going to be s times s over s squared plus omega squared minus cosine of 0. What's the cosine of 0?
1.
Beautiful. Equals minus 1 over omega. I'm just going to put this s squared over s squared plus omega squared minus 1. Minus 1. Let's form a common denominator. S squared plus omega squared minus s squared plus omega squared over s squared plus omega squared. Focus inside the brackets right now. Don't worry about outside the brackets. Focusing on inside of the brackets, I still have minus 1 over omega on the outside. Inside of the brackets, common denominator, s squared plus omega squared, and watch the beauty. S squared minus s squared. S squared minus s squared. They cancel. Minus omega squared. Minus omega squared. This negative out here cancels with that one. One of these omegas cancels with one of that. And here it is. Sine of omega t. Laplace transforms into omega over s squared plus omega squared. Okay, that's wonderful. Example, I want the Laplace transform of 6 cosine of 3t plus 2 sine of 3t. So that's going to be equal to 6 times the Laplace transform of cosine of 3t plus 2 times the Laplace transform of sine of 3t. And now let's just plug and chug. 6 times s over s squared plus 9 plus 2 times omega 3 over s squared plus 9. Interesting. Equals 6s plus 6 over s squared plus 9. Okay, that was very cool. Now, we can look at higher order differentiations, and I don't want to go too far on you with higher order differentiations, but let's at least take a look at how we might do this. Higher order differentiation. In the time domain. So we really don't want this so much for functions, believe it or not, that we know. We want it for functions that are just given functional names. Okay, so let's see. So we know f of t transforms into f of s. Let's start with that. Let g of t equal f prime of t. So what do we know? G of t transforms into g of s, but we know g of s is s times f of s minus f at 0. We know that. I'm sure, I hope all of you are looking at this and saying, oh my God, initial conditions. That's what you should be thinking. That's right, initial conditions built into the Laplace transform. Okay, now let's look at g prime of t. So let's let h of t equal g prime of t, which we know is equal to f double prime of t. So h of t Laplaces into h of s, which is equal to s times g of s minus g at 0. But g at 0, don't forget, g at 0 is equal to f prime at 0. Right? Because g of t is f prime of t. G of 0, f prime at 0. So that tells us that h of s equals s times g of s. S, f of s, minus f at 0, minus f prime at 0. So we started off with f of s. First derivative, I get s f of s minus f at 0. That's the first derivative. Second derivative is this one. It's this, which is this, s squared. I get an s. Every time I take a derivative, I get an s. Does that sound vaguely familiar to you? Where did we see every time we took a derivative, we get another s? S squared, S cubed, S to the fourth. Where did we see that? Characteristic equation coming from the differential equation. This is all tied together. It's the same S. So this would be first derivative, second derivative. What do you think the third derivative would look like? The third derivative of f. What do you think the Laplace transform is going to be? That's not even, I don't even need those parentheses in there. 0. Well, that was cool. I got a delayed reaction here. S squared f of 0 minus s f prime of 0 minus f double prime of 0. So here's the proof of the general form. The Laplace transform of f, and this means, in parentheses, means the nth derivative. Nth derivative. And that is equal to s raised to the n power times f of s minus s raised to the n minus 1 of f of 0 minus s raised to the n minus 2 of f prime of 0. And then we're just going to continue down, minus dot, 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 minus f, the n minus first derivative evaluated at 0. So we're going down in powers of n, we're going down in powers of n, and we're going up here in derivatives of the f function. Keep in mind the lowercase f functions. Everybody understand the difference between capital F and lowercase f? Does everybody understand that difference?
Yep.
Okay, these lowercase f's are the time domain function. The uppercase f is the frequency domain function. So this is for any nth derivative. Now, if you're scared looking at that, we are barely going to expand beyond the second derivative. Okay, for the most part, we want the first derivative. We don't generally need more than one derivative. But watch the following example. And I think you can understand the power. And for those of you who have had differential equations, you should recognize the following. Okay, so I have this differential equation. Actually, let's just change this differential equation. I'm going to change this. Instead of having a 0 over here, I'm going to get rid of that 0. And we're going to put a function over there, a function that we know. So how about e to the minus 6t? I like that better. Okay, so here's what we're going to do. We're going to Laplace transform both sides. Okay, I'm going to remind you on the left-hand side, this is the Laplace transform of I double prime plus 3 times the Laplace transform of I prime plus 2 times the Laplace transform of I, and that is equal to Laplace transform of e to the minus 6t, 1 over s plus 6. Now, in general, what you and I are doing is we're solving for what is the function I that satisfies this differential equation. And this is how we would solve for it. I is a function and we don't know it, but we do know the following. We know the Laplace transform of I, don't forget this, the Laplace transform of I is I of s. So we're going to put it in there. So that's true. What's the Laplace transform of I prime? Well, it's equal to s, I of s, minus I at 0. What's the Laplace transform of I double prime? It's equal to s squared, I of s, minus s, I at 0, minus I prime at 0. Oh my goodness, let's put that all in there. Here we go. S squared, I of s, minus s, I at 0, minus I prime at 0, plus 3 times s, I of s, minus I at 0, plus 2 times I of s equals 1 over s plus 6. Let's group all my I of s terms. Watch this. S squared plus 3s plus 2 times I of s. Does that look like the characteristic equation for this differential equation? Yes or no? So that's that term, that term, that term. Now all I'm left with are these other constants. So let's see what they are. So I at 0 is 1. So this is minus s times 1, minus s.
Should that not be s squared plus 3s plus 2 I of s?
Yes, thank you. Thanks, Jack. So minus s for that one, got that one. This term, I prime at 0 is 2, minus 2, got that one. And then this one is minus I at 0 times 3. So I at 0 is 1 times 3 is minus 3. And all of that equals 1 over s plus 6. So we're not going to spend a lot of time solving this because we don't know how to, but certainly we can do the following. S squared plus 3s plus 2 times I of s equals 1 over s plus 6. And then I'm going to add all this to the side, plus s plus 5. And what we would do is we just form a common denominator over here. And that's going to look like the following. S plus 6. And then I have 1 plus s plus 5 times s plus 6. Okay? And then to solve for I of s, divide both sides by that. And that's how you solve for I of s. We'll leave it there. But that's how you use this on differential equations. That's how it's used. All right. That was the fourth property. There are a number of properties. They're all pretty important and pretty valuable. So let's get on to another one of our properties that we want to look at, and that is the property for integration in the time domain. Again, not responsible for these proofs that I'm showing you, just responsible for the result. If f of t, Laplace transforms into f of s, Well, let's see. Integration is the opposite of differentiation, correct? So what happened? What was the basic thing that happened when we differentiated? We multiplied by s. What do you think is going to happen?
Divide by s.
Correct. Divide by s. The integral from 0 to t of f of tau d tau. That is going to Laplace transform into f of s over s. You're probably sick and tired of seeing me integrate by parts, so I'm not going to integrate by parts. We're just going to leave that alone as a property. Okay, and we'll just deal with that as a property. So we can use this property if we know a particular function's Laplace transform, and we know one function is the integral of the other. That would be like the ramp function is the integral of the step function. So we can look at the Laplace transform of the step function, and then we can take that and divide by s to get the integral of the ramp function. 1 over s divided by s is 1 over s squared, and sure enough, we already know that to be true. Okay, this one we're not going to use a lot in this course, but it's an important property. It's a time domain shift. And I want to show you this proof because I want you to see what I'm talking about when I say you've got to recognize certain things in the forms of these functions. So if f of t is a Laplace transform that's f of s, then f of t minus a, u of t minus a, Laplace transforms into e to the minus as. We saw that with the impulse function, the shifted impulse function, times f of s, provided a is greater than 0. Same reason we talked about before. We've got to make sure that we're shifting into the area that we're taking the integral of. So I have a certain function, and that certain function, I'm gonna draw this function so that you can see this function like that, okay? Now, if I shift this over to a, so I have a certain function. Now, if I shift this by a units, so let's just say this here is b, I'm going to shift it by a units. What's going to happen is b will go this direction by a units. Okay? Now, here's the problem. When we calculated, if this is f of t in red, when we calculated the one-sided Laplace transform, we calculated it by ignoring this. Everybody agree with that? We didn't do anything with that because we integrate from 0 to infinity. So when we do the shift, we can't just shift this function over, because if we just shifted the function over, it will look like this, for example. And we can't take all of this because we didn't include this part in the integral. So we don't want to include this part. So when we shift it, we shift only the part for t that was greater than 0. And that's what this does for us. It throws away everything that was over here. That's why it's there. If you're wondering why it's there, that's why it's there. Let's look at this proof. This proof is a pretty cool looking proof that helps us, again, recognize a form of an integral. So here we go. Now let's call it the proof first. Proof. Laplace transform of f of t minus a, u of t minus a is equal to the integral from 0 to infinity, f of t minus a, u of t minus a, e to the minus st dt. Now, by the time you're seniors, hopefully you'll have seen a lot of this and you're going to know exactly what to do. So this one is not an integration by parts. This is definitely a u substitution. So here's what we're going to do. I'm going to let u be equal to t minus a. Because this is a problem for us. We don't know what to do with this, and that's a problem for us. So we're going to let u be equal to t minus a. By the way, since there's a t over here, I need to know what t is equal to. So t is equal to u plus a. Don't forget that. T is equal to u plus a. Okay? So du is equal to dt. Du dt is equal to 1, and then the derivative of that, that's a constant, it's equal to 0. So we're going to substitute all of this in. So this equals the integral. Now I have to change my limits on the integral. So the lower limit is 0. The new limit, u, is 0 minus a. Is that correct? The t value is u plus a. Okay, so this is on t, the t value. Is that good? We got that? So what we're going to do our substitution. We're going to end up with, first of all, from this, in this integral right here, this u of t minus a, where does that integral start? What can we can replace this with the number 1 inside the integral, correct? But that function is 1 from where to where?
0 to infinity.
Almost. Look inside here. U of t minus a. And a is a positive value. So it shifts it to a. So this function is 1 from a to infinity, correct?
Yeah.
Okay, so from a to infinity, now I'm going to get rid of the u of t minus a. So I leave the f of t minus a, the e to the minus st, and then the dt. Okay, so we're going to take this value of t here, and we're going to convert it to a u value. And here's how we convert it to a u value. We convert it here. So we take this value, I take the a value, I substitute it in here. It's a minus a, and that gives me 0. And then I plug in that for t. So infinity minus a is equal to infinity. Over here, I have a t minus a, but t minus a is equal to u. So this is all f of u. And then I have e to the minus s, and I have to substitute t. Here's t here, u plus a, all times dt. I'm sorry, all times du. dt is equal to du. This is my integral is on u now, no longer on t. I had the integrals on t, it's now all on u. I'm going to manipulate some mathematics, 0 to infinity. F of u, e to the minus su, e to the minus sa, du. What is a constant inside of that integral with respect to u? What is a constant inside of the integral with respect to u?
The e minus sa.
Equals e to the minus sa. I'm going to bring that out. The rest of it, 0 to infinity. We're right on time. F of u, e to the minus su, du. Don't forget, u is a dummy variable. U can be x, it can be dog, it can be jack, it can be t, it can be anything. What is all of this here?
F of s.
Beautiful. And so our result is that when we shift, what happens when we shift in the time domain, a shift in the time domain equates to, believe it or not, a shift in the time domain equates to multiplication by a complex exponential in the frequency domain. That's bizarre. It's not obvious why that happens, but we're going to see some duality properties later on that shifting in the frequency domain causes something to happen in the time domain. So we'll leave it at that. We're working our way through properties. We're going to spend some more time. This is a deep chapter with regard to all the things that we want to do with Laplace transforms. So we're halfway through our week this week. I'm not sure if we're going to get through everything I want to in this chapter in the next 2 lectures, but we've got a lot of material. We have to finish the Laplace transform properties, and we have to do inverse Laplace transforms. And once we talk about that, then we're going to have to talk about partial fraction expansion. And then we have to do the partial fraction expansion with Laplace transforms, and then use lookup tables to figure out the whole answer. So that's all coming as we're moving forward. Any questions before we part for the day today? Okay, you're responsible for the results, not the proofs. In this class, I'm not going to ask you to prove anything. I used to do that years ago. I'm not going to ask you to do that. Not in this class. We'll have another class where you have to do those things. Just focus on the results, how we use the results to move forward with Laplace transforms. Stay safe, everybody. Stay away from people. Have a good rest of your day. And I'll look forward to a good day off for you tomorrow and seeing you again on Thursday. Take care.